course, after having noticed that it's machine crypto. But Boiling himself refused to talk about much of how exactly he did the analysis, remarking stuff like, well, a magician doesn't reveal his tricks and stuff like this. So this whole talk presents a plausible reconstruction only. It's based, I might add, on 2 books about this topic. I will tell you which ones in the end, where everything is explained in much more detail. Okay. So you should keep that in mind, that this is not certain. When I write in the following, well, from this it is clear, and you see here, and blah, 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 it means, well, we think that probably this is what he did. Okay. So let's look at an example of one of these intercepts, what they would look like. You see here, this is the ciphertext, or actually it starts with plain text. Here, it's German for here, and stuff like this, blah, 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 blah. And you see these digits in the middle, in between the words. These are not ciphertext, these are just abbreviations. I will explain them in a second. The digits, remember, they mean the special characters. So if you see 3, 5 in the intercept, it means it's a letter shift followed by space. It's actually just meant to be a space, but the operators had the habit. This is going to be important in a moment. The operators had the habit of pressing 3 and 5 consecutively to get a space, because, well, it would ensure that the machine was in letter shift for the next word. Because sometimes the line noise would cause the machine to erroneously switch into figure shift, and you wouldn't be able to read anything. And this habit kind of suppressed that. You would be sure that you're again in letter shift for every new word. Okay, so you see here. This is written out without the special characters. So you see here MBZ QRV, and then we have a 5-4 here. That makes the I think, does that make the 5-4B? 5 is a space. I forgot that down here, but okay. And 4 figure shift, and B is probably the code for the question mark. And then it goes on, 3-5 space KK, 3-5 QEP, blah blah. And then figure shift again, and lots of stuff. These are these numbers, and then you get to the end, blah blah blah. Here 3-3-5-5, lots of spaces, and then you get and VV. And these are the codes that switch the machine into crypto mode. And after this, everything becomes garbled. This is actually the ciphertext. You see one more space, and then ciphertext. Let me explain the abbreviations shortly. Here I said it means here. MBZ is the name of the sending station, and QRV was a standard abbreviation among, well, teleprinter operators and maybe also in radio operators, which means just do you read, like do you understand. This will be important in a moment also, because this is a word that was used very often for obvious reasons. And KK is just for German klar, clear, everything's okay. So, oh yeah, also notice that this is intermingled. These are the 2 stations talking in alternation. So you see, this is here MBZ QRV, do you read? And then the other station responds okay. And then you get this QEP, blah, blah, blah numbers. This is, I can tell you, this is an initial vector, basically. It's the part of the crypto variable that changes. So this is what one of the stations says, okay, let's switch into crypto mode with these initial parameters. And then it says which means umschalten, switch over. And WW means verstanden, understood. And this exchange, one station says the other says WW, and this would automatically switch the machines, or maybe semi-automatically, I don't know, but it's not important. And then they would talk in the secret. Yeah, okay, so you can see what is likely to be used for an attack. Well, I said the QEP numbers represent an initial vector for the crypto. You have one part of the crypto variable of the key, which is secret among the stations. It's probably distributed over other channels and changed once a day or once a week or so. And then you have the IVs, these QEP numbers that would be added in order to avoid sending the same message with the same key, or a different message with the same key, I mean, right? Because that's the problem with the stream ciphers. You don't want to send different messages with the same keys. So, okay, so what would happen is that the operators would reuse the same QEP numbers, and then you could just exploit that, which you will see how in a second. So, and then we've already seen the frequent use of typical sequences, the 3-5, obviously, and also QRV is very common. And this will be important because you can assume that it will also be common in the ciphertext. Okay, so now let us suppose that we've actually received a bunch of intercepts that were a bunch of crypto messages that were indeed encrypted with the same key. So on the same day with the same QEP numbers. As a side note, this was actually not so uncommon because the machines in the beginning had a technical, like a mechanical or design flaw. The machine had an actual reset button that would reset it to a certain preset state. And the operators would often do this just out of because it's convenient. For example, if your line noise garbled your state, the machines get desynchronized, and everything has to be reset somehow. And then they would just push this button, the machines would be reset to the original state, and they would go on. And then you would have a different message, maybe a little bit different, maybe a little bit more, but with the same key. So you could expect to get lots of these actually messages, as it's called, in depth. When you get more than one message with the same key, then it's called a depth, or at least in the jargon of the time. So let's assume we've got these, and a number of others. I only show 4 here. This is not enough for the whole analysis, but it won't fit. So you'll just have to accept them as a little, yeah. I have a paper version of the talk where you can see the whole example with, I think, 10 messages, and you can look up the details there. Okay, so we've got these messages which we know nothing about. And they are again, but we can look for stuff that appears a lot of times. Especially B graphs. That means that is 2 characters after another. So, for example, we have UM here. UM. It appears a lot of times. This is one thing you can't see in this because it's only 4 messages. But if you look at the 10 messages in the paper version, you would see UM appearing a lot of times. You would see ZGJ1 appearing a lot of times. You see here already ZGJ1 is here, and it's again here. And here's UM, and WF is also one that would appear lots of times. This is something you'll just have to believe me now. And well, what you can do is you can just guess that, well, these repeating B graphs are probably 3-5s in the plain text, because, well, to repeat a B graph, that's, well, to have a B graph at the same position in 2 different plain texts is not so common. And so in order to get the same ciphertext also at the same position, you would have it gets much more unlikely. So if you do see that the same ciphertext appearing over and over, it's very likely that it must be a B graph that is very common, that appears very often. So that's why you can assume here these are probably 3-5s. You also see these are 3-5, one after another. This is something that was done in the example here. You see 3-3-5-5 or something like that. It could happen. The operators would just repeat stuff in order to make sure that it went over correctly. Okay, so we've got these little assumptions here about plain text, and now we can look further. And well, what we can do is we can guess that it's a substitution. No, it's an XOR cipher, because this is what, well, I said was common or already known at the time, and so this would be our first guess. Well, this implies the characteristic weakness of XOR ciphers, which is that, well, if you the plus here is an XOR, okay? This is addition modulo 2. So and if M and M prime are the two ciphertexts, you XOR them. Well, the keys cancel out here, right? You've got this is the first message with the XORed with the key stream. This is the second message XORed with the key stream, and well, it has an associative law, and it has and it commutes. So you can pull the key over here, and it cancels out. So you get just A plus B is the same as M plus M prime. Okay, this is just a characteristic when using this kind of cipher, and well, you can just check if it holds to check your assumption, your guess. And in fact, in our case, it doesn't. So the machine is not exactly using an XOR cipher, but it almost does. If you do it, you take, for example, the 3 and the 5, and the U and the G, encrypted with the same key. That means encrypted with the same key means they appear at the same position in the messages. If I go back a little, you can see here. If you look at one column, you know, at this point, if these messages were encrypted with the same key, so at each column the machines are in the exact same state, unless they take input from the plain text as permuting the state. But this is another. This I think was not common at that time, and well, you can just guess it, and then you will find out that it all works out. So let's assume that after in each column the machines were in the same state. So you can look if you find a U and a G and a 3. No, if you find in the plain text 3 and 5, and in the or like here, and you see in the ciphertext a U and a G in the same column, you know, because of this characteristic, that if you add the U and the G, the ciphertexts, and you add the 3 and the 5, the plain texts, then you should get the same thing, right? Okay, so that's what we're checking here. We take the U and the G and get this, and we take the 3 and the 5 and get this, which is almost the same, just that it's permuted somehow. It looks pretty much the same, just the 0 has moved around, and maybe the 1s have also moved around, which we can't see, but we can see that the 0 has moved. So, and if you do this for other examples, then you will find that they all show the same effect. You can look for other characters that also, you know, add to something which has only a single 0 or a single 1. Then you will see the exact same effect on all of them. So you can guess further that, well, maybe it's not an XOR, but maybe it's an XOR followed by a permutation. So this is the hypothesis that Beuerling made, that you get the ciphertext message by, well, first super enciphering with a pseudo-random key stream, and then applying a certain random permutation sigma. Okay, let's check our hypotheses, or actually, well, just as a side note, at this point, it's not entirely clear whether the permutation is done before or after the super encipherment, right? It could also be that you first permute the plain text and then XOR, or it could be the other way around. But we're going to, I'm going to tell you right now that